formed. So you are going to have a gold film applied to the bottom of substrate for reflecting as much light to the surface of the device. So you know that when the photons are going to be formed, they will try to come in the backward direction. So if you are going to have a reflecting coating here, these photons will again be reflected back and they will go to the front. So this avoids the photons from escaping from the backside. So below the N type, you have substrate. Below the substrate, you will be having a gold layer, which will ensure that maximum reflection is provided for the photons, and photons can come out only from the P side. They cannot escape from the N side. So that is the reason why you have a gold coating below the substrate in your LED. That is what is discussed here. You can see. So your gold film is applied to the bottom of substrate, so which will ensure that the photons are reflected back to the P type, and only from the P type layer you have the light emission happening. So LEDs are always encased to protect the delicate wires. So the efficiency of LED will increase with the increase in the current and decrease in temperature. So you know that as we have seen, that when the forward bias current is larger, the brightness of LED is also larger, right? So the efficiency of LED will depend on two parameters. One is the injected current, and second one is the decrease in temperature. So when the light is concentrated near the junction, as the carriers are available within the diffusion length of the junction. Okay, so with you know that the diffusion length is very small because of forward bias case. So the carriers are readily available within the diffusion length for recombination. So the different LEDs emit different colors such as red, green, yellow, orange, blue, and white. Some LEDs emit invisible light also. Invisible means you have infrared and ultraviolet. Okay, so in the WIBGR spectrum, you know, violet, indigo, blue, green, yellow, orange, red. So in the WIBGR spectrum, outside violet you have the ultraviolet, and outside red you have the infrared. So some LEDs are going to emit light in that spectrum also, which is not visible to human eyes because of the wavelength. Okay, our human eyes can visualize only these basic colors. They cannot see the infrared and ultraviolet rays. So LEDs can emit different colors, and if you want to have a different color LED, you have to change the material. So if you use different material, you will have different light emission happening from the LED. So the wavelength of emitted light depends on the band gap of the material. So what material you are going to use will determine the emitted wavelength, light wavelength. Okay, so the color of the emitted light will depend on the material. If you use gallium arsenide, you will have infrared radiation. It is invisible to human eyes. So if you use gallium phosphide, you will have red or green light emission from the device. If you use gallium arsenide phosphide, you will have red or yellow. So you can see here the different combination of group 3 and group 5 elements which are used here, and the corresponding color is also mentioned here. And LEDs are very delicate devices, and they are operating in forward bias. You know, in forward bias the current is enormous, right? So if you have to protect the LEDs, you have to have a series resistance of 1K or 1.5K must be connected in series to the LED always. So remember, LEDs are delicate devices and they are operating in forward bias, and you know, in forward bias the current forward bias current is very high, right? So it will damage your LED. So for that only, all the LEDs in any circuit, if you see, the LEDs will always have a series resistance of 1K or 1.5K, which will ensure that the LED is not damaged at any cost. So when you are going to reverse bias your LED, it will not emit light. Okay, it will not work in reverse bias. So LEDs generally operate between this voltage 1.5 to 3.3 volt. The current will be in the tens of milliamperes. The current will be in the order of milliamperes in a forward biased LED. So the power requirement is typically from 10 to 150 milliwatt to the lifetime of 1 lakh plus hours. So LEDs can work for 1 lakh plus hours without any damage. And LEDs switched on and off very fast. See, the switching time is 1 nanosecond, which you cannot even think of. You cannot measure this 1 nanosecond because it happens very quickly. So LEDs can be turned on and turned off very fast. It is not like your electrical fan, which takes some time to attain the maximum speed. No, When the moment you instantly turn on your LED, light starts emitting, and it looks like the process instantaneous, but after 1 nanosecond the light emission takes. That 1 nanosecond is very very small for you to visualize that. Okay, and LEDs are used in many applications. You can see they are used in burglar alarm systems, picture phones, multimeters, calculators, digital meters, microprocessors, digital computers, electronic telephone exchange, intercoms, electronic panels, digital watches, solid state video displays, and optical communication systems. So LEDs have a huge application area where they are incorporated. Also, there are two lead LED lamps which contain two LEDs, so that a reversal in biasing will change the color from red to green and vice versa. So your two lead LED lamps are available which contain two LEDs. One will emit light red and one will emit green. So by changing the biasing, you can definitely change the color from green to red and red to green accordingly for display purpose. So when the light emitted is coherent, essentially monochromatic, then the diode is called as laser. So in LED, the light emitted is not coherent, which means each photon will travel in its own speed, and each photon will be traveling randomly. So the light emitted from LED is not coherent, but if you claim that the emitted light is coherent, then the device is called as laser diode. It is called as injection laser diode. So two sources of light we have in optical communication. One is LED, other one is injection laser diode, LED and ILD. ILD is injection laser diode, and depending on the application we'll be using LED or laser. So LEDs, lasers are very quick. They have a shorter rise time than LED, which will make it suitable for high data rate application. So when you're going for a larger bandwidth and larger data rate, the laser becomes an obvious choice of your source because it has a very short rise time compared to LED. And also using laser, you can couple a larger amount of power. That's why they say you should not see the laser light with your normal eyes, because the power is very high such that it will damage your retina. But the light from LED is not such intense that it will not cause any damage to your eyes. But the light from laser is very coherent and intense in power, which is not advisable for human beings to see it with your normal eyes. So this high generation LED can be used for long distance transmission. And one drawback in LED is the strong temperature dependence. So temperature effects will make your laser diode not a suitable candidate if it is going to be operated in a very high temperature or a low temperature regions. But your LEDs don't suffer from that problem. But injection laser diode are having a strong temperature dependence, which will ensure that as the temperature is going to increase, these devices are going to become unstable. So that drawback you have in your LEDs. Okay, so LEDs are going to have a non-coherent light emission, but laser diodes are going to have coherent light emission, and lasers are going to have very short rise time when you compare to LED. So this short rise time property of lasers will make suitable candidate for wide bandwidth and high data rate applications. And also the high power which is available from the laser diodes can be used for long distance communication. Okay, and one drawback of ILD is that it has a very strong temperature dependence, whereas your LEDs don't have that drawback. Okay,